Hi, this is Dr. Holly, and today we're going to talk about design by contract. This engineering design technique is at the foundation of how we design and implement software. The main points that we're going to talk about today are systems thinking and design by contract. There are a number of terms and concepts that we're about to discuss. You may want to get out a piece of paper and pencil and take notes. The main idea behind systems thinking is that there is an interface that separates the inside from the outside of a system. And, given this interface, we want to discuss the roles played by implementers and clients with respect to the system. So, let's jump right in with systems thinking and get the details all straightened out. A system is anything that you identify or want to think about as an individual unit. And the interface is the boundary that separates the system from everything else. And it also provides a convenient way in which to think and reason about the system's behavior. Here is an example of a system: the ice and water dispenser built into the front of the refrigerator. The dispenser's interface includes a way for a client to choose between water and ice, and with ice provides the option of cubed and crushed. A pivotal idea in systems thinking is the ability to build larger systems out of other systems. These internal systems found in a larger system are referred to as subsystems or components. Going back to our refrigerator example, we see that the ice and water dispenser is indeed a subsystem of the refrigerator. In fact, this unit has multiple subsystems, including a refrigerator, a freezer, the dispenser, the ice maker itself, etc. Once we have identified a system and its interface, we can now talk about the client of the system and the implementer of the system. The client is a person or agent that views the system from the outside as an indivisible unit. The implementer, on the other hand, is a person or agent that views the system from the inside and is responsible for implementing the system, oftentimes by assembling a number of components or subsystems. In the context of software, the implementer of a system often writes code by utilizing the other operations as subsystems by making calls to them. Two engineering techniques are utilized to describe the behavior of a system: information hiding and abstraction. Information hiding is a technique where information about how the system works is intentionally left out of the description. For example, the fact that there is an ice maker somewhere behind the ice and water dispenser does not need to be part of the description of the ice and water dispenser. Abstraction is a technique where a coherent cover story is created that allows the client to effectively reason about the behavior of the system by explaining the system's behavior from an outsider's perspective. Now we introduce design by contract. When designing a software system, an effective organization must have policies that govern the design process. Design by contract has become the standard policy in modern software engineering organizations. Fundamental to design by contract is how it captures two very important concerns related to software: what it does and how it does it. Keeping these concerns separated when engineering a piece of software is of utmost importance for items such as software correctness and software scalability. At this point, we need to dive into some of the details needed to better understand design by contract. The first is the use of models. A variable in a piece of software has a programming type, and that programming type has a corresponding model that allows us to describe and reason about the behavior of the variable. We are going to use these models to support information hiding and abstraction when describing a systems interface. Two mathematical models that you are familiar with are integers and real numbers. Because we have studied concepts related to integers as far back as learning to count, we often do not realize that these concepts are part of the math model for integers. We use these concepts to model the behavior of a piece of software that makes use of programming integers. Because we know how addition works in mathematics, we know in general what the addition operator does in a piece of software, but not necessarily how it does it. Whereas our mathematician colleagues have precisely formalized mathematical integers, other variables that we will want to have in our programs will not necessarily have a formal model on which to rely. In cases like these, we will rely on informal concepts for modeling the behavior of these programming variables. Each of our operations will have a contract that comprises a precondition and a postcondition. Preconditions are often stated in writing using what's known as a requires clause, and postconditions are stated as an ensures clause. An operation's precondition states the requirements that must be met prior to a call being made to that operation. These requirements involve the values of the parameters being passed to the called operation. An operation's postcondition dictates what the code that implements the operation must do. And again, this can involve values of parameters as well as the value returned by the operation. There are two situations that can arise when an operation is called. The requirements of the precondition are met by the calling operation, and the requirements of the precondition are not met by the calling operation. When the precondition is true at the time of the call, then the called operation will terminate with the conditions in the postcondition being satisfied. On the other hand, if the precondition is not true, then the called operation may do anything, including not terminate. With respect to this contract, there are responsibilities and rewards. Making sure that the precondition is true at the time of the call is the responsibility of the client. The reward is that the client may assume that the postcondition is true when the operation returns. Also under the contract, the implementer of the operation has the responsibility to see to it that the postcondition is true when the operation returns. The reward allows the implementer to assume that the precondition is true when the operation is called. Remember, an operation has 0 or more formal parameters which serve as placeholders for information being passed to the operation. And if the operation has a non-void return type, then the operation will return a value based on that return type. The job of this operation is to compute the square root of a number declared as a double. The requires clause indicates that the x and the epsilon parameters must be positive. The ensures clause indicates that the computed value returned must be greater than or equal to 0 and fall within a tolerance based on epsilon. In the ensures clause, the computed value is represented by the name of the operation. Those are the letters S, Q, R, T. And the mathematical square root is also represented. It is represented by x raised to the 1/2 power. When reading the contract, the requires clause and the ensures clause refer to the operation's formal parameters by their name. And if the operation returns a value, then the ensures clause refers to this value by using the name of the operation. To determine if the precondition is true, then at the time of the call you must substitute into the requires clause the values of the arguments for the respective formal parameter names. And for the ensures clause, substitute the value returned by the operation for the operation's name. Here is a tracing table example. We use tracing tables to trace through the execution of a piece of code. The table has two columns, column 1 for the code that we want to trace, and column 2 to indicate the program state, i.e., the values of variables in the program. In this example, the code shows a call to the operation's square root, with the local variable y to receive the value returned by square root. Since the only variable in this program is y, the row just before the call to square root we see has the value 79.6. Question: what will be the value of y after the call to square root returns? The answer: y receives the value of 2.0 from the call to square root. This is the same tracing table as before, except for now we have two local variables, y and z. Prior to the call, y equals 79.6, just as before, and z contains the value for which we want the square root, which is 4.0. Notice that z now appears as the first argument to square root in the code. Question: what will be the values of variables y and z after the call to square root returns? The answer: y receives the value 2.0 and z remains unchanged. Now we have two questions. Did the client satisfy the requires clause? To determine this, substitute the values stored in z for x in the requires clause. Also substitute the 0.01 for epsilon. And you see the answer is yes. X's value and epsilon's value are both greater than 0. So we have a responsible client here. Now the benefit to the client. The client can assume that the value returned by square root will have the positive square root value for 4.0, the first parameter. So the answer to the second question is yes. Finally, notice how we are able to reason about the behavior of square root without knowing its implementation details. That is, without looking at its code. We've about come to the end of this session. Here is a list of some terms introduced today. We cannot have an intelligent conversation about software design and implementation if you don't know instantly what these terms mean. So, get to work. Finally, the two main points covered today are systems thinking and design by contract. The main idea behind systems thinking is that there is an interface that separates the inside of a system from the outside of a system. And given this interface, we discuss the roles played by a system client and a system implementer, and how the requires and ensures clauses allow us to reason about the behavior of an operation without knowing how it is implemented.